Okay, let's talk a little more about the hat matrix. So I'm going to start with a matrix fact. If a matrix is symmetric, that means that the matrix A equals A transpose. So being symmetric means that you're the same as your transpose. If a matrix is idempotent, that means that A transpose times A is equal to A. So basically when you square that matrix, it's equal to itself. So these are just some matrix facts that probably you saw maybe in linear algebra or in a previous class, but they're important ones to remember. And the reason why this matters is because the hat matrix, H, is both symmetric and idempotent. And I'm going to use that fact in a second to basically help solve the application exercise that you all did in class on Tuesday. So let's first show that the hat matrix is symmetric. So we're going to show that H is equal to H transpose. So here's my H, X times X transpose X inverse X transpose. And what we're contending is that that is equal to X times X transpose X inverse X transpose transposed. So let's pull that transpose through. If we transpose this, then we end up flipping the order and adding a transpose to each piece. And so this guy ends up over here and this guy ends up over here and both end up getting transposed. If you take the transpose of a transpose, you end up back at yourself. And so we end up with X, X transpose X inverse, X transpose. And voila, that's the same. So we've shown that the hat matrix is symmetric. So that's good. Now we need to show that it's idempotent. So that means that if we multiply the hat matrix by itself, we get the hat matrix back. And so because we know that the hat matrix is symmetric, we know that this is the same as saying the hat matrix times the hat matrix is equal to the hat matrix, because the hat matrix transpose we just showed is the same as the hat matrix itself. Okay, so let's plug those in. So we know the hat matrix is X times X transpose X inverse times X transpose. So that's the first H. And then let's write it again, X times X transpose X inverse times X transpose. So that's our HH. And now let's add our hat matrix on the other side of the equation there. All right. So this part here, this X transpose X times X transpose X inverse, that's going to be the identity matrix. As we know, if we multiply a matrix by the inverse, it ends up with being just the identity matrix. So we can just cancel that part out of the equation. And we're left with X transpose X inverse, X transpose. And so there you have it. We've got H on this side and H on this side. So that shows that H transpose times H is equal to H, or that the hat matrix is idempotent. Another fact is that I, the identity minus H, is also idempotent, and you can show this pretty easily using the same techniques that I've shown you here. And I might practice doing that on your own. That may come up along the way. Okay, so the next fact is that the trace of the hat matrix is P plus 1. So let's go through that, why that would be true. So here's the matrix facts that I showed before about traces. The trace of a square matrix is written as the trace of A, and it's the sum of the diagonal elements. Some important facts are that if you have the trace of A plus the trace of B, you can pull that through, so you can separate that out into just the trace of A plus the trace of B. If you have the trace of C times A, so the trace of a constant times A, you can pull that constant out. And if you have the trace of ABC, you can mix up basically the order of the matrices on the inside, and those will all still be equal. So we're going to use these facts here to solve the trace of the hat matrix. So let's plug in the formula for the hat matrix, X times X transpose X inverse X transpose. Let's take the trace of that. So the first thing we can do is, per that third fact, we can reorganize this. Because as we showed, with the trace of ABC is equal to the trace of CBA is equal to the trace of BCA. Basically, we can mix up the order of the matrices on the inside. And so I'm going to use that fact, and I'm going to pull this X transpose, and I'm going to pull it out to the front. So I'm going to move it over there. And why am I going to do that? Well, now I have a very easy matrix here. This is the identity matrix. And so this X transpose X times X transpose X inverse, we know that equals the identity matrix I. And the reason why this is important is because I is the easiest matrix to take a trace of. If you remember what I is, it's just a matrix with all zeros on the off diagonals and 1 on the diagonals. So the trace of the identity matrix is always going to be equal to just the sum of that diagonal, which, because those are all 1s, will be equal to the dimensions. So the identity matrix is always going to be square. And so the dimensions there then are going to be the same for the rows and columns. And so you could use either the rows or the columns. But that number, so for example, if this was an n by n matrix, then the trace would be n. Okay, so let's figure out the dimensions of this I matrix here, because by just seeing I, we don't actually know what those dimensions are. So let's try to establish what those are so we can guess what the trace is. Actually, we don't have to guess, we can know for sure. Okay, so in order to do that, I'm going to first remind you that X here is a design matrix. And so this design matrix has dimensions n by p plus 1. So n because there are n observations here, and p plus 1 because there are p predictors and 1 column of 1s at the beginning that is used for the intercept. So n by p plus 1. And so if we look at this set of matrices where this I comes from, the first one is X transpose, so that's going to have p plus 1 by n dimensions. The second is X, and so that's going to have n by p plus 1 dimensions. And so if you multiply these together, you end up with p plus 1 by p plus 1. And X transpose X inverse, that's going to be p plus 1 by p plus 1 as well. So when you multiply these matrices together, you end up getting this identity matrix that is p plus 1 by p plus 1. So what does that mean for the trace? Well, that means the trace, if you have p plus 1 rows and p plus 1 columns, then that means you have p plus 1 1s on the diagonal. And if you add all those up, then you end up getting p plus 1. So the trace of this identity matrix is equal to p plus 1. Okay, so we're going to use that in just a minute, but I just thought we'd sort of build up to this. All right, so first let's solve this first part that you were tasked with on as an application exercise last time. So we wanted to show that the residual sum of squares, which we can write as E transpose E, these are those residuals, and we want to show what that is equal to. So I am going to first split this out into y minus y hat transpose times y minus y hat, because I've just filled in what the definition of the residual is. And we can replace these y hats with hy, because we know that the hat matrix puts a hat on y, so if we multiply y by h, we end up getting y hat. So I've just replaced my y hat with hy here and my y hat with hy here. And now I'm going to pull out this I minus h. And so basically what I'm doing is I'm pulling out the y here. And so if I pull y out, I end up with I, the identity matrix. This is sort of like if we were pulling a constant out of a scalar, we'd end up with 1 minus h. But because we have a matrix here, we're going to use the identity matrix in that spot. So I minus h times y. So these two are equivalent. And we're going to do the same thing here. We're going to pull the y out of both of these. And so we end up with I minus h times y. Okay, now let's pull this transpose through. And so if you remember, when you pull the transpose through, every piece on the inside ends up getting the transpose, and it flips the order of the matrices. And so we end up with the y transpose in the front, and then I minus h transpose. And then this next part stays the same, I minus h times y. Now, if you remember from what I had told you about the idempotent rules, I proved that h is idempotent, and I also told you that I minus h is idempotent. And so what that means is that I minus h transpose times I minus h is just going to be equal to I minus h, and so we can replace that here. So now we have the residuals is this residual sum of squares is equal to y transpose times I minus h times y. So that was what we were trying to get to, and we've done it. And the reason we wanted to get it into this nice form is because that allows us to easily take the expectation of this quantity and use some of those rules that I had shown you last time. So let's go on to do that step. So I asked you to take the expectation of the residual sum of squares, And that's going to be equivalent to taking the expectation of y transpose times I minus h times y because of what we just showed on the previous slide. And so just to remind you of this matrix fact and the reason why we wanted to get it into this nice format, I told you last time that the expectation of some matrix X transpose times some constant C times a matrix X is equal to the expectation of X transpose times C times the expectation of X plus the trace of C times the variance of X. Okay, so let's use that fact here and split this out. So what I've done is I've applied that exact fact to this data. So I'm now showing that the expectation of Y transpose times I minus H times the expectation of Y plus the trace of I minus H times the variance of Y. So all I've done is taken this form and I've applied that fact to it. Okay, so now we know that the expectation of Y is X beta. And so the expectation, if we take the transpose of that, we end up with beta transpose X transpose, because when we take the transpose of something, it flips the order. And then we still have the I minus H here. And then we plug in for the expectation of Y, X beta. So this part should be pretty straightforward. And now this next part, so we're taking the trace of I minus H times the variance of Y. And we know that the variance of Y is sigma squared. And we can actually pull that out because if you remember from the trace rules, if you have a constant, a scalar, you can pull that out of a trace. And so like that scalar C, little c that I had in the trace rules got pulled out, kind of like this sigma squared gets pulled out. So this gets pulled out because it is both a constant and a scalar, and so it can come out front. And then we're left with just the trace of I minus H. Okay, so let's deal with this side of the equation first. So I'm going to distribute this x beta to each part of this I minus H. So when I multiply x beta by I just get x beta, because when you multiply anything by the identity matrix, you just get the original matrix back. And then I'm going to multiply this x beta also by H. And so I end up with beta transpose x transpose times x beta minus H x beta. And so H here again is that hat matrix, plus sigma squared times the trace of I minus H. Okay, now let's expand this out a little bit so we can see what's actually going on here. So now I'm just expanding this H term, so this hat matrix. And so now instead of writing H, I'm going to plug in x times x transpose x inverse, x transpose times x beta. And let's look a little more closely at this part right here. So this, on the inside, here is x transpose x inverse times x transpose x. And so that's just going to be the identity matrix, because when you multiply a matrix by its inverse, you end up getting the identity. So that cancels out. And so what does that leave us with? That leaves us with x beta minus x beta on the inside here. And so that's going to be 0. And when you multiply something by 0, it cancels out. So this whole first part of the equation just ends up being 0. So now we're left with sigma squared times the trace of I, the identity matrix, minus H, the hat matrix. And so coming back to thinking about when we're taking the trace of something, well, first let's mention that when you take the trace of I minus H, so when you're doing addition or subtraction with a trace, you can separate those out. So instead of taking the trace of I minus H, I can write this as the trace of I minus the trace of H. And so that's a nice fact. I can pull that trace through. And the other fact here is that if we can determine what this identity matrix, what dimensions it is, because of what an identity matrix looks like, it's just going to be, we can use those dimensions to determine what the trace is. Because again, the identity matrix is going to be just a matrix with zeros on the off diagonals and ones on the diagonal. And so whatever the dimensions are, that's going to be the number of ones that we're adding up when we're taking the trace. And so here, this identity matrix is n by n. And that makes sense. I mean, we can look at it a couple of different ways to try to think about why this is an n by n matrix. But the easiest way is to just think about kind of what's getting multiplied here. We've got this y, which has n rows. So it's got one for every observation. Well, in this case, it's got it has n columns because it's transposed. But the y itself has n rows. And so this identity matrix on the inside here is going to be n by n. And so that's what this is here. So that tells us that the trace of a n by n identity matrix is just going to be n. So we can replace that with n. So now we have sigma squared times n minus the trace of h. And we just worked out the trace of the hat matrix recently, and so what was that? It was p plus 1. And so now we've shown that the expectation of the residual sum of squares is sigma squared times n minus p plus 1.